We are going to talk. I will first talk about what is the Diaphora, how it works, and why I wrote it back in the day. And then Pancake will explain what were the problems and what are the use cases that can be used with radar Diaphora. Okay, so it's an open source GPL project. It is more than anything focuses on patch diffing. For example, finding how a vulnerability was fixed in a closed source product. Also for porting symbols between different IDA databases. This is the second main scenario why I wrote such a tool, and also for finding new functionality in a closed source product. Plagiarism detection. There are many use cases. So basically, I wrote it myself back in the day because Dynamics BinDiff, which was the tool that I used to use the most for this kind of things, was on support. Google bought the company Dynamics, and they didn't continue supporting it anymore. Well, the slides don't look better. Okay, I will skip this part because it doesn't matter. So, the internals. Basically, the Affero simply does the following. Export the word radar, right now, or IDA database to my own invented SQLite format. Then it compares all the artifacts, the things that I extract for each function from each binary that we analyze. And then issue SQL queries just to determine how similar they are or to find matches between two databases or more databases. For now, if you want to use Diaphora for batch analysis, for batch diffing, or as you want to call it, you need a GUI, something that is not well integrated right now in Radar. So for now, if you want to see the results, you have to use IDA. So how it works? When we are talking about exporting, it is reading each function in the database, and then all their attributes like the flags, the prototype, relative addresses, number of basic blocks, edges, stuff are recorded. All basic blocks and their attributes, the instructions and the relative attributes of each instruction, and many more other data, like for example the pseudocode or the AST abstract syntax tree, in case that you have the compiler of each function, etc. Then, for each function or basic block, also some information is calculated, not just extracted. Like a hash based on the bytes, the non-changing bytes of each instruction. Like if we have, say, a jump that is relative for the stuff, we will have the bytecode for the jump, and then I will remove all the bytes that are changing, because it's a relative, it's not a relative, but a fixed jump or something like that. For example, the cyclomatic complexity, which is a measure used to determine how complex looks like a function. The strongly connected components of the flow graph. This is a graph-based theory. The topological sort of the flow graph, the MD index, and other things related to the graph. The small primes product. For each strongly connected component, I will explain a bit later what is a small prime product. As well as a set of 3 fuzzy hashes of the raw pseudocode text, another fuzzy hash that I invented myself, based on the abstract syntax tree, supposing that we have the compiler and many other things that are calculated. So, as I said, for each database, the following information is calculated, and also a fuzzy call graph has based on the small primes product of its function cyclomatic complexity. Yeah, I know it is not very easy to understand. So for each function, I calculate the cyclomatic complexity, how complex it looks. It simply will return a value like 5, 0, 2, 10, 20, whatever. And then for each function, what I call the small primes product is, depending on the function cyclomatic complexity that I assign, let's say that it is 5, I take the 5th prime number, and then all the prime numbers of all the functions are multiplied together, and that very big number is the hash for the call graph, what I call the small primes product hash. Blah, 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 blah. This is useful, for example, when you don't want to do comparison function per function, so you just compare the last hash. So you can determine if structurally the binaries look pretty much the same. Okay? So comparisons. When we have two databases that are exported from IDA or radar to the SQLite format that is understood by Diaphora, SQL queries are launched to find function matches. The SQL queries launched try to match as much arguments or match artifacts as possible using different heuristics. As of today, we have like 49 heuristics, I think. First, I launched the most robust ones, the ones that generate the less false positive numbers, and then I continue launching the less reliable ones. For each match, a similarity ratio like 0.1 unreliable, 0.999999 very reliable is calculated for the match. And then they are labeled as either best, partial, or unreliable. Unfortunately, yet, as of today, we cannot see the results with the radar because we still don't have an independent GUI. So if you want to see results, you have to use IDA for now. So, as I said, oh, no, 49, 47, anyway, some of the heuristics, so you can get an idea, is, for example, equal or similar assembly or pseudocode, both raw and cleanest up. With cleanest up, I mean, like when we are calling a function that we don't know, I simply remove the name of the function, and it doesn't matter if the number of the name of the functions that are being called are different, as the pseudocode or the assembler is actually the same. Removing the parts that are variable, it says that the functions look very similar. Byte has names, the same function name, especially useful for doing patchy diffing. All or most attributes from the function, if we have like, say, 30 attributes that we calculate or extract from its function, and 27 of them are actually the same, we can most, I think, conclude that it's a good match. Same address, nodes, heads, and primes, that's it. The instructions, it doesn't matter if they are reordered or not, are actually the same in both functions. So we know that it is actually the same function. Import name has, a bit complex to explain, pseudocode fuzzy hashes, and the pseudocode fuzzy AST has a hash that is fuzzy, so it causes collisions based on the abstract syntax tree, supposing that we have the compiler. Okay, then, as I said, for each match that the SQL queries give, a similarity ratio is calculated 4 methods, but in the screen we can only see 3. So trust me when I told you the last one. So basically, I do a quick ratio, matching the pseudocodes and matching the assembler of both functions, and I get a measure like 0.1 or 0.99999, whatever. The same, but cleaning up the pseudocodes or cleaning up the assembler, as I previously said, if we have, for example, in the pseudocodes, variables or function names, I simply remove the names. I don't care about them. And if we have variables or offsets or whatever, I remove the names. So what we are comparing is out of variable names, function names, offset names, whatever, and we can pretty much compare and out, and I do the same again, a quick ratio calculation that will give me a value between 0 and 1. Then the different ratio based on the small prime products, again, of the abstract syntax tree, in case that we have the compiler, and the last one is the MD index. The MD index is an index generated for flow graphs that was invented back in the day by Eero Carrera, Rolf Rolls, Halvard Flake, and stuff. Oh yeah, it was here. Okay. So according to ratio, the matches are grouped in a set of either best, partial, or unreliable results. Partial results are those that have a similarity ratio bigger or equal to 0.5. Anything below is either partial or unreliable. Heuristics. I will briefly explain some heuristics. As previously says, there are many heuristics used by Diaphora. Some of them are very simple, others are not that simple. Some of them are very reliable, like, for example, getting all the bytes from a function. If we have a match 1 per 1 with a big function and all the bytes match, it is a perfect match. while others are not that reliable. If I'm removing the functions and I'm removing the variables and stuff, and then we have a very small function that matches everything, but when we remove it out many things, it's a very unreliable result. So some functions, some heuristics, sorry. Byte has and names. So it simply compares the non-changing bytes, as I said. Let's say that we have a jump to somewhere. I remove the bytes that tells where you have to jump of each instruction, and the references true names. True names is an IDA thing. A name in IDA is whatever that was assigned as a name by IDA. It can be a function, it can be a string reference, it can be a global variable somewhere that has a name. So the name, like a function name or a string reference with a name that is not generated by IDA. If it is generated by IDA, I simply remove it. And if the hash that I calculate from the byte hash and the names is actually the same between two databases, it is a very reliable measure to determine that they are similar. This is how a heuristic looks like. After all the data is calculated at export time, which is the most crucial, most important thing that we do in Diaphora, we simply run SQL queries against the database. This one is actually the byte hash that I set, and it is. Here we have an array, which is simply a column with all the names found in the first database and in the second one. So if the bytes hash that I calculated and the names are actually the same, and the names are not empty, we have something, we can conclude that the result is good. Another. This one is one of the most common one in program diffing tools, and I think that is the one that is implemented in every single diffing tool that I have seen. But Diaphora have many heuristics that other tools don't have, like doing the same but cleaning up. Cleaning up is a fancy way of saying I'm removing stuff, doing fancy hackings in the code, removing variable names, global names, label names, and stuff. The pseudocode fuzzy ASD hash is like, do you know SSDIP? Similar to SSDIP, calculating the SSDIP hash, well, not SSDIP, but something similar, of two texts. If the final resulting text is the same, we conclude that it looks pretty much the same, both at assembler and at pseudocode level. The strongly connected components in graph theory, strongly connected components are like, for example, let's say that we have a function with two loops. We will have two strongly connected components, the first loop and the second loop. It is a way to determine, to try to match different graphs from different functions. Okay? This is what I explained before. This is how it pretty much looks. Here I am using IDA. As we can see, we don't have label names. Everything is XXXXX, whatever. We don't have labels that we are jumping, or we don't have even global variables or local variables on anywhere. What I do is simply remove everything. It is what it was called engine errors. Yeah, it was an antivirus, if I remember correctly. I simply remove everything. This is how it looks, the proper code, and this is how it looks when I clean it up. We can ignore this part. This is unfortunately another heuristic that is very good, but unfortunately only available as of today in using IDA, because we don't have a great support in radare2 for now for a nice decompiler. Actually, writing a decompiler by itself is a big project. So what I do, I take the abstract syntax tree, a tree that defines all the syntax of the function that we are decompiling. To each instruction, like an if, a do, a while, a switch, a goto, whatever, I assign a prime number, and like I did before, I simply multiply all the prime numbers, it's a small primes product, and I get a final big number that is a hash based on the abstract syntax tree of that function. If we have a match one-to-one between two databases, we can determine that looks like the same function. Okay? Strongly connected components, I explained it before. Switch structure, this is another thing that we still are missing when exporting from radar. What I do in IDA is, let's say that we have a switch that takes the value case 1, case 2, case 3, case 4 default. The constant that are used for a switch case can be very determinant or can be very interesting to determine if two functions are actually the same. If we are talking about 0, 1, 2, or boring stuff, probably the match is not very good. But let's say that we are comparing with some specific constants that are rare, that are not very common. It will give you a very good and rare match that probably you cannot match in any other way. Before, when I implemented it, I was researching antiviruses, and I thought that it would cause a lot of false positives. But when I started comparing with antiviruses, I realized that it did not cause that much. So it's one actually of the reliable ones. Okay, there is no demo time for this, sorry. So future, before Pancake continues. So the current status, in my opinion, but well, in the outro, what I'm going to say, is the best open source or otherwise program for doing program diffing as of today. Back in the day, it was bindiff with no doubt. As of today, adopt bindiff is better. If you have the decompiler, it's the only one that is going to make use of the decompiler. And I have a few changes on mine that eventually I will implement. So more heuristic will be added eventually when I need it more than anything. And some of the ones that I'm still trying to determine is, for example, using an intermediate language. This is why I was interested in ESIL. So I take the intermediate language translation of some function, then I apply optimizations over it, like the compiler will do, and then I compare the optimized versions of the intermediate language. It doesn't matter if you are comparing set 80 or ARM or Spark or whatever. As you are comparing finally the optimized version of an intermediate representation, I hope that the results of comparing both will be pretty similar. I hope. One of the ideas that I do for doing that is either using ESIL, but it's a bit limited yet, or using libvex. Libvex is actually what is used in Valgrind, and is used since long ago, and it supports a bunch of platforms, and is well tested in production. So GUI changes. So far, we only have one GUI. That GUI is for IDA. We don't have a GUI where Diaphora integrates for example, radar, or if we want to port it tomorrow to binary ninja or to Hopper or whatever other tool. Yeah, it's not possible to Hopper, but anyway. So one of the ideas is to create an independent GUI so we can export from whatever tool we prefer to choose, and then use that GUI to do diffing and to actually even read the source. You cannot believe, back in the day I used it to work for Heuristics, and you cannot believe how many people ask you for a read-only application to read databases in iPads or things like that. I don't know why, but people ask for it. Another thing, but this is like maybe someday if I have a lot of time. So another thing that I pretend to do is finding matches between source code and binaries. Basically getting out the abstract syntax tree using clang of each function of a source code base that you give to it, and then it tries to compare the ASTs of the compilation and the AST of the source code. I don't know if it's going to work. If I ever finally implement it, I will tell you. But it will be very useful when you when you are analyzing a closed source product, but you have partial source because it was leaked back in the day or things like that. And for this use case, it's pretty useful, but it's not trivial to implement. Actually, it is easier to work with binaries than with source code, in my opinion. So that's it. Diaphora is open source. You can do whatever you want with it. It even supports radar now. And now Pancake is going to talk about the nightmare that it was porting Diaphora to radar. Your time.
Yeah. Thanks. So now I will talk about the way that I have been integrating Diaphora into radar2. This was less than 1 week of work, so it's more like some kind of proof of concept. So the thing works, but it's not perfect. It's far from complete. But you can use it to understand how to port one tool that works with another program like IDA or so on into radare2. So why it matters to support radare2? First thing is that it's an open source tool. It's available everywhere. You can use it in batch mode. You can use it in product. You can use it anywhere. And the thing is that you can modify it. You can create your own plugins. You can support many other architectures. And it's pretty handy for testing stuff because it's like there is a command line that it's pretty handy for testing things, and you don't have to spend a lot of time like analyzing everything. You can just load or analyze a specific part of your program that you want to compare, etc. I will also explain how to use this, a little bit about the internals. I will explain a little bit the problems or why the tool was so integrated into IDA API, so I had to make some kind of wrappers of the IDA API to call radare2 comments. And the format of the SQLite, because the output of this analysis is generated into a SQLite database. And then about the visualization and future. So who we are, he already presented himself, and I guess that I don't need to make the presentation again. So the reason for this is mainly, as I said before, because science. Mainly for headless analysis, you can automate things, you can run it in remote machines, you can use it for comparing the results of different tools. So I would like to compare the analysis of IDA with the analysis of radare2 to see where are the things that I'm missing, or compare different analysis of radare2 to see the differences in different programs and using different options for analysis to compare the results. Also, it was an interesting playground for creating a wrapper of the IDA API. So it will be possible at some point to have like a full IDA API on top of radare2. So you can just use the IDA scripts into radare2. And show a little bit how easy it is to create these things on top of r2pipe. Some of the most common use cases, or the ones that it comes to your mind when you start using diffing tools, is for malware indexing, which is something that it's already done in Maltinder, a project of Hussein, which is an open source tool project that it's basically analyzing malware and finding common stuff between different malware. So you are not looking for families, or not looking for similar things, but which kind of malware things share some functions from another one, which is quite interesting because you end up having your own conspiracy theories. It's also interesting to see the changes when for example, there is a bug fix because there is an upgrade for a specific application or driver that they are fixing some vulnerabilities. You can have the previous version and the new version, and you can use this tool to find which is the changes between one version and the other one. Also for automated one, because you can have you can always do these kind of things by hand, but when you have a large number of binaries to analyze or to compare, it's always better to have these kind of things automated. And there are so many other cases, so just think a little bit on that, and you will probably have more ideas for using and integrating these kind of projects. Okay, so how to use this tool? Diaphora, it's written in Python. There is two different Python scripts. One of them is the one that creates a SQLite database out of a binary. So you have like one binary or one library. And then you specify like there is a Diaphora lowercase lower dash IDA.p, and then you specify the file name you want to analyze, and this will generate an output.SQLite file. And you can analyze this with SQLite, and if you have like some patterns, you can just select and type some SQL queries to understand what's going on. And when you have two SQLite databases, you can just call the Diaphora.py and pass the two SQLite files, and then it will generate a new SQLite file, which is the diffing results of that. So there are two different SQLite formats, or two different schemas for the two different databases. And at the end, visualizing the results, as Hussein said before, there is no open source or portable front end, because it depends on IDA, the current one. So right now you have to use your brain, just doing some SQLite queries, but it should be pretty easy to make I mean, you can use SQLite browser to browse the different results and so on, but it should be pretty easy to make like a web front end, some kind of Node.js or Python web server exposes this information in a web application, and you can just browse the results. That will be pretty easy to do, but I didn't have time for that.
Actually, the output resulting database, when you do the diffing, you have tables like best matches, partial matches, and reliable matches. So you just need to display the data. That's it. You don't need to understand very well the format, because you have the same columns that you will see in the AIDA GUI. So at least for watching in their final results, it's all be like pretty easy, but we haven't done it, sorry.
In order to install the Diaphora, you can use r2pm, so just type r2pm-i Diaphora, and this will install, well, it will clone my fork of the Affero repository, which is the one that supports radare2. It hasn't been merged in the main repository yet. And it will put two scripts into the path. One of them is Diaphora, and the other one is Diaphora-2, R2. The Diaphora R2 is the one that will analyze the binary, and the Diaphora one is the one that is diffing the two SQLite files. In order to call this from radare2, you have to specify, you can do it in two different ways. One of them is in batch mode, so you can just Python Diaphora R2 and then the path to the file. This will spawn a new instance of radare2. And after that, it will run a bunch of commands to generate analysis and then create the SQLite file in the output. But you can also reuse some project or some analysis that you have done in the binary. So you can just type dot space and then the Affero lowercase r2. The script will detect that it's running inside radare2, so it will not perform any analysis. And this will reuse all the function information and code analysis that have been done before to generate the SQLite database. So let's talk a little bit about the internals, and I will make a quick demo so you can see the current state of the thing. So what I did for doing that was basically taking the Affero Lodash IDA Python script, and I was basically removing code, all the part that was doing all the graphical part, mainly because the current implementation is just a single script, a very large one with all the stuff mixed inside. There is no library for importing this. There is no separation in different files. So porting this was more or less just removing code and changing some parts and writing functions for replacing the implementations. I was basically running the script until I got a Python exception, and then I was implementing the function that was missing. And most of the problems that was having is that the current IDA API code was depending on IDA objects and functions. So in order to replace this, I had to write the IDA functions, the signature, and then return some objects, so fake objects emulating the IDA objects, because I was not being able to, I was not using IDA at all, so I didn't know how the API was working. I was checking the documentation. I was basically returning the objects that with filling with some methods and fields to make the Affero happy. And also I added some functions that was prompting the user for some questions, like do you want to remove the database before creating a new one, etc. Right now the IDA API support is just for what I needed for this, but it will be possible to create, and it's planned to create a separate Python module that you can use from any other project, that it will be able to reuse the IDA scripts to run on top of radare2. And let's check how the SQLite format is and so on. So this is a script. It's a Python script, and it's like 2,000 lines script. At the end, you can see that there is like the main. I'm basically checking if there is the r2 pipe lodash in variable set. This means that if it's set, I'm running the script inside radare2. This is the variable, the minimum variable that is set by radare2 when you're running from inside radare2. And this environment shows the file descriptor that it must use for using the pipe to communicate with radare2. There is the in and out, and one for reading comments from radare2, and the other one is for writing the result. So when you want to run one command, you will basically check these variables. That's what r2pipe does internally. And it will write the command with a null terminated string, and then it will get the null terminated string from the other file descriptor. After that, if it's running inside radar2, I will just call open without any parameters. So I will get a session loaded for the current running session of radar2. I will get the file name. And if not, I will basically query the user with a message help saying that you have to specify which file you want to analyze. And then it will run a bunch of commands in order to set up the configuration for doing all the stuff. The current configuration that I'm using is just disabling the flags, the bytes, removing the color, because I don't want to compare colors and I want to have like a more compact SQLite format that only matters about the text representation of this assembly. I also enable the EO catch because if I'm emulating some parts and I want to write some stuff, I don't want to modify the final binary or have some errors in output. And I have also enabled the has next option, which is handy for some kind of analysis. As you can see here, there is a bunch of changes here. There are some commented lines. AAA was one of the tests that I did. Then I tested with AAB, then with AAC. And here's the hard-coded AAB one, which is the fastest way for analyzing a binary and getting most results without doing too much things. Then it will basically query the user if you want to create a new database, etc. So let's see how this thing works. We can just code it like this. I will use CP. I will create a SQLite database out of the /b and /cp binary, and it will run from inside radar2. So I'm reusing the current session. It will not spawn a new session of radar2. It's querying me if I want to remove the database. I say that yes, and the analysis have been done, and it has been doing all these lines in order to show what's going on inside the Diaphora. Diaphora basically takes the base address where the binary is loaded, and it will subtract all the offset for all the basic blocks and functions, ops, strings, etc. This is basically because then you don't have to work with huge numbers. You can just work with smaller numbers. And this is also handy when you are comparing kernels, because the addresses in kernels are quite huge, and it's better to compare like small numbers. Other things that are interesting to see here is that, well, apart that there is so many debug printfs in there, is that it's taking the control flow graph of all the functions, and it's generating a text representation out of that. So now we have an SQLite database that we can open here. Here is all the tables that are created. We can see the results. So here is all the functions, and it creates one row for each function, and it creates a bunch of information for each. So there is, like, for example, here is the disassembly. You can see the XXX that Hussein said before, that it's replacing all the labels from there. There are more things to improve in this database or in the way that radar2 exposes the information, but more or less it works. I mean, I've been comparing some basic binaries, and I was able to identify where the problem was. Some of the issues that I found is that for small functions was not finding any change, because it's assuming it's a false positive, or it's assuming that there is no real change in there, mainly because there is not enough information to determine that the function is valid or not. Like all the imports things, that it's just 1, 2, 3 instructions, that all the small functions that are like returning some value or doing a small math operation. We can do, for example, this, and then we can analyze another binary, like maybe sleep. And then we have two SQLite databases, the A and output. We can rename these to b.sqlite, and then we can run Diaphora passing the two binaries, the A and B. This will generate an A versus B database, which is, again, another SQLite database. And if we check, there is less tables in here. One of them is results, which is probably the most interesting for us. And we see that there is only one result, and we can check also the unmatched, which is so many more unmatched functions in there. Here is this 1.000 is the ratio of matching between the two functions that have found in one of the other binary. So how to visualize this? I started writing this small script, which is a Diaphora view. But as you can see, it's just the beginning. It's like an import, it's opening the database and doing some queries, but doing not too much more. And the idea is to generate an HTML file, a static HTML file that you can just open and see the results, like listing functions, the matches, adding some colors depending on the ratio of matching, etc. But I said, I think that just using a web user interface will be probably the best way or the most easy way for doing these kind of things, because you don't have to mess with native code, or you don't have to mess with widgets of one operating system, or that doesn't work or doesn't look the same in another one, or don't depend on huge frameworks. So it just, you can use the web anywhere. So future. What can be done or what should be done to make this project improve in the next weeks, months, years? One of them is the performance. Python is probably not the best language for doing something that must perform. R2pipe is probably not the best way for doing something that must perform, mainly because there are other ways, or I mean, you can just use the API, the C API directly, or just using in C++ or Rust. Also, Diaphora could be re-implemented to not be done in Python, or just refactor it in order to be more maintainable or easy to port to other tools. Also, the user interface with options, because the IDA front-end have many options for doing different analysis changes and diffing changes that right now it's hard-coded for the R2 implementation, just to have like a working version without too much queries and questions. Better visualizations, because you can make graphs and 3D representations and virtual reality and stuff like that. And also, it would be nice to integrate these kind of things into radare2. Radare2 supports his own diffing engine, but it's not as complete as the Affero. And it's always nice to have more support for different tools and scripts, because this way you can just compare results and find bugs and make all the tools better. It's also interesting, or it would be cool to have some kind of community around the project, not just about the Affero, but also about the Affero R2 and having more people testing it and using it for their own needs. Having a test suite is probably one of the most important things when you are trying to make something reliable or big, because if you are upgrading the tool and you are generating new databases or new analysis from different binaries and they don't match with the previous ones, you will probably have a lot of false positives or some information that it's not correct. So having a test suite is probably very important. Also create a server database. So you can, instead of just having everything in file system, you can have like a service that is just providing information about, so you provide the hash of the binary and you get the SQLite out of it. So you can just hold only small parts or small amount of binaries in your local, and just query the server for having other ones. And maybe port to other backends like PU, etc. Questions? Ideas? If not, that's all for me. Thanks.
Thank you.